In example 3, we've got an open top rectangular box that is to be constructed from a square piece of cardboard that is 18 inches on each side. And we're going to cut squares out of the corners of equal size and then fold up the sides. I want to find the volume of the largest box that can be made this way by basically determining how big should the squares be that we should cut out of the corners. So to illustrate this, because it's a little hard to visualize, here we've got, stop it, background, we've got a square piece of paper. Okay, so what we want to do is like rip out, I don't know if you may have made a box like this in, I don't know, your childhood. I think I did. This will be done in a more exact way, but I'm basically just ripping out some corners of approximately equal size here. So they're squares, so they're the same on either side. And if you do that on all four corners, you get this shape. And then if you fold up each of the pieces that are left, get this 3D shape that does not have a top to it. We call this an open top box. And this has a volume now because it's 3D. So if I cut out maybe larger squares from each of the corners, we might get, we get a different size box with a different volume. It would be taller. If we cut out really tiny squares, we'd be, the height would be really short. It'd be a shallow box with a different volume. And we want to know, without wasting a bunch of paper, what size of the squares that we should take out in order to maximize the volume of this box. Okay, so the thing that is changing here, right, again, is the size of the squares that we cut out of each of these, each of the corners. So, again, rather than wasting a bunch of paper to figure this out, we can use mathematics to model this and calculus to find the volume that is the largest. As always in these problems, I would suggest that you draw a picture first. So we can start by just drawing this square piece of cardboard. So I'm just going to draw a square. And it says that it's, when we start, it's 18 inches on a side. So I'm just going to label that. So this here, this length is 18 inches. And then this length here is 18 inches. And in fact, all of them are 18 inches, but the ones across from each other are the same. So a square, 18 inches on all sides. Now we're going to cut out these little squares in each corner. And I don't know how big these squares should be, so I need to assign a variable to that. So I'm going to call this length x, which means that the width of this square will also be x. And that's the same all around, right? This will be x here. This will be x here on all four of these squares. They're all the same so that it folds up into a nice, box that fits together. So all of these have to be the same. Now we want to start thinking about the volume of this box, because that's what we want to find the maximum of. So we want to maximize the volume. Volume is a 3D measure. Volume of a box is found by multiplying length times width times height. Okay, so how do we go from this flat piece of paper up into 3D and find the volume, the length and the width and the height? Well, if we think about what happened here if this was size X, then when we fold up the box, it actually becomes the height. So let's draw a picture of what this would look like when it gets folded. So I'm just going to kind of sketch a picture here of my box. So it might look something like this. And again, the height here is going to be X. So that's what that, whatever size we cut out, that corresponds to the height of the box. Now the length and the width of the box, which are basically the length here, that is what's left over after I take out the two corners. So in our picture, that's these lengths here. So this orange dashed line will be what we get when we fold up. So this orange dashed line is where that would go down here. This length here, we have to determine what that is. So if the whole thing is 18 and we take away 2 squares of length X, then what's left over here is going to be 18 minus 2X. Okay, so I'm going to label that here, but when we fold up these sides, that becomes what that length is there. This length, or the width, or one of them's length and one of them's width, we know this is height. So if this is length, then the width is over here. That will correspond to this distance. Now this is a square, so that distance is going to be the same, right? The whole thing here is 18, and we're taking away 2 x's. So this will be 18 minus 2x as well. So that pink dashed line, when we fold it up, becomes the width or the length, whatever one you want to think about it as. That side in our 3D figure is the 18 minus 2x. In our 2D figure, right, the orange ones and the pink ones are equal. In fact, they're all equal, but if we didn't start with a square, they might be different. So I think that's all we really need to know in order to find a formula for the volumes. We've got length, we've got width, and we've got height. So if we multiply all of these together, that's going to give us the volume. So we'll have 18 minus 2x times 18 minus 2x times x. Or if we like, we can write that as 18 minus 2x squared multiplied by x. Now in these questions, we often have a constraint or something that limits our, our values that we can have. Our thing we want to maximize here actually is already in one variable. And remember that the constraint normally allows us to eliminate one of the variables that's in our formula that we want to maximize or minimize. Here we already have just x's. So the constraint, we actually don't have one in this case. Other than the fact that we started with a square piece of paper, we don't have a constraint. And again, we don't need one because our formula is already in one variable. So we can just go ahead and differentiate this. So we want to use derivatives, or use derivative to find the maximum volume. So we would like to differentiate the volume equation. All right, so let's take a look at the volume equation here and think about finding the derivative of this. You could expand this out. You could just FOIL it and then distribute the x. Or you could use the product rule. Just for practice, I'm going to use the product rule on this. And so let's see, so v prime, product rule says first times the derivative of the second. So first is 18 minus 2x squared. The derivative of the second, the derivative of x, that's 1. Then we add the second, which is x, times the derivative of the first. Okay, so the derivative of this stuff here, that's going to need the general power rule or the chain rule. So we're going to bring the 2 down and multiply. We'll leave the base the same. We subtract 1 from the exponent to give us 1. Then we have to multiply by the derivative of the inside, and that's -2. All right, I know I'm going to want to set this equal to 0, so I should probably try to factor it. I'm going to leave this as 18 minus 2x squared, but I don't need the 1 there. I'm going to multiply x and 2 and negative 2 together to give us minus 4x. And I'm going to leave that 18 minus 2x intact because I see that it's in common and I want to factor it out. Okay, so we can take out a GCF of 18 minus 2x. Right, what's left over here is an 18 minus 2x to the first. And what's left over here is a minus 4x. Then we've got negative 2x minus 4x, so we can combine those together in that second factor there into 18 minus 6x. All right, we would like to set this equal to 0. We did all of the hard work already by factoring this. When we have a product set equal to 0, we would like to just set each factor equal to 0. So we're going to take the 18 minus 2x, set that equal to 0. Okay, let's see what that gives us. Let's add the 2x over to the other side. We'll divide by 2, and that gives us x equals 9. And we'll do the 18 minus 6x equal to 0. I'll add the 6x over to the other side and divide by 6. And that gives us x equals 3. All right, so here we've got two different numbers. One of them might be a maximum and one of them might be a minimum. If you stop and think for a minute about what one of these actually would mean, one of them doesn't really make any sense. If we were to cut out squares of size 9 on each side, then that would mean we would cut out our x here would be 9, but the whole thing is 18. So we would cut out something of length 9 on this side, but we also have an x over here. So we would be cutting out basically the entire piece of paper if this were 9 and this were 9, right? Because that would give us 18. And we would essentially have no paper left to make a box. So I hope that this one will give us a minimum, and hopefully this one here will give us a maximum, but let's let the calculus decide that. So we want to verify which one gives us a maximum volume. Okay, so let's find the second derivative, so v double prime. I'm going to look at the first derivative as a product right here, and I'm just going to use the product rule on this. Okay, so we'll take the first times the derivative of the second, which is negative 6, plus the second, 18 minus 6x, times the derivative of the first, which is negative 2. This is fine, but if I just, expanded this and distributed everything, I don't know where that x came from. That should just be negative 2. Sorry, so if we distribute the negative 6 and the negative 2 into the parentheses here, we'll get something that's a little easier to work with. So let's see, 18 times negative 6, that'll give us negative 108. Negative 2x times negative 6 is positive 12x. Let's distribute that negative 2. 18 times negative 2 is negative 36. And negative 6x times negative 2 is positive 12x. And if we just simplify this even further, negative 108 minus 36 is negative 144. And 12x plus 12x is 24x. Okay, now remember we're going to use this to check out the concavity at each of our critical numbers. So we're going to plug in a 9 into the second derivative and see what we get out. Is it positive or is it negative? So negative 144 plus 24 times 9 gives us a positive 72. So remember that's positive, positive, that's concave up. And so that means that we have a minimum. We don't want that. So let's ignore this 9. In the other case with the 3, when we plug that in, cross our fingers, hope we get a negative number out. Let's see, that comes out to be negative 72. All right, great. So that means concave down, And so that means that we have a maximum. So that x equals 3 is the size of the squares that we'd like to cut out. I think we want to actually find the volume of the largest box. Okay, so we know the size of the squares that we should cut out. So let's see. So this means that we should cut out squares of size 3 by 3. Uh, 3 inches by 3 inches. In order to find the maximum volume, we should just plug that 3 into our volume equation. So the original volume equation was 18 minus 2x squared times x. So v of 3 will be 18 minus 2 times 3 squared, and all of that times 3. 2 times 3 is 6. 18 minus 6 is 12, so this will be 12 squared times 3. Oh, 12 squared is 144, and then let's multiply that by 3. So 144 times 3 gives us 432. Now, because this is something measuring something, we want to make sure we've got units. So volume is always cubic units. Everything's measured in inches, so this will be cubic inches. Here we go. This is the size of the biggest box that we could make using this technique. So go ahead and make one of these, store some stuff in it, and have some fun. I've got one more example for you, so tune into that, and I will see you.